Welcome to the part B of this second lecture, which will be about ordinary differential equation approach to solve SIR models. So going to the deterministic SIR modeling approach, in part A, talking about the Reed-Frost model, we were looking at a stochastic model, but now we turn to the point where we think that the population which we consider is so large that it's sufficient to disregard stochasticity aspects of the epidemic process and use a deterministic model. And this model was already used by Tom in the first lecture, but I'll briefly cover parts of it again. So the SIR model can also be formulated in a continuous time deterministic setting. And here deterministic means that whenever you know the input, you will know the output. There's no random component into all of this. And every time you simulate, let's call it that, such an epidemic, the result will be exactly the same. One way to formulate this is using ordinary differential equations. We will look a bit more into that. And you can say in a general setting, such a deterministic way of modeling is trying to model the mean of an underlying stochastic system. For small population sizes, this is actually not true by the deterministic differential equation model, but for a large population, you can show that you converge towards the mean of a stochastic version of the SIR model, which we will look at in part C. So again, we will consider only a closed population, no demographic turnover, no input, no output, no imported cases, and so on. And the population is assumed to have a fixed size, capital N. Just as a motivating example, we will look at an outbreak of classical swine fever virus, which happened in the Netherlands. So this is classical swine fever virus is a very contagious disease which occurs in pigs and wild boars, and of course always there's also the interaction between these two populations which is of interest. Characteristics of the disease are symptoms after infection are dullness, anorexia, and in acute form is rapid mortality, often without clinical symptoms. So and secondary symptoms are diarrhea and respiratory problems. So you can say for pig production, such a disease is a huge problem, and the question is how you can try to control such outbreaks once they occur. And in fact, you try really hard to try to minimize that you have such outbreaks. So here's the data which I've taken out from a publication where the data are provided. It's a huge outbreak which occurred in the Netherlands in 1997. There are 429 infected herds. So herd is a community of pigs, for example, by one production facility, and they were stamped out. So more than 700,000 pigs were killed, not only because of the disease here, because they died of the disease, but also because the herd was infected, and then you stamp out the entire population in order to ensure that it doesn't spread on from there. So more or less 700,000 pigs were stamped out here. And additionally, 1,286 herds were preemptively slaughtered. That means that there was no disease detected so far at the farm, but because they were close to a farm which had a disease outbreak, they were stamped out as well. So that was approximately another 1.1 million pigs which were stamped out as part of that. Just to get a nice idea of the size of the total pig population in the Netherlands, and the Netherlands is a big pig producer, there are about 22,000 herds altogether. So it is substantial, but not all of them which were affected. And of course, you will always be interested in trying to investigate, are such preemptive measures, are they really worth the costs or the lives of that many pigs? So this is also, of course, an analysis that you'll be interested in doing. So looking at the data here, I report the number of new infectious herds. So I don't look at the number of pigs in particular, but I look at the number of newly reported infectious herd. And and that is based on contact tracing and serological analysis. So you see that it grows initially, and then it levels off, and then it fades out slowly, and then you have a bit of remerging at some point. And it's weeks after first infection, so that meant that this outbreak went on for over a year. Okay, and recapitulating stuff that Tom had explained in his lecture, we will divide the population into 3 groups: susceptible, infectious, recovered, and we will assume a closed population. That means at all times S plus I plus R is equal to the total population, and even in the beginning we will assume that S naught and I naught will be equal to N. And we will use an ordinary differential equation system to describe that. So the first is the dynamics in the number of susceptibles. So given that we have a particular number of susceptible and a number of infectious, we have this nonlinear interaction term between the two. So you can always think of this. Let's consider one susceptible individual, and what we will have is that you have the rate at which you are in contact with other individuals is given by B. So this is the contact rate, but it's not only the contact that you have where you meet somebody, but it's also the rate at which you have infectious contact. Please be aware that you can more or less divide contacts that you meet somebody, but then condition on that you meet somebody also what is the probability that you transmit the disease. And this is in this case here put together in this one parameter beta. So you say, okay, for this one susceptible, I will meet other individuals, say susceptibles or infectious. At this point, it doesn't matter with the rate of beta, but how many infectious individuals will I then meet? Well, that's beta times I of t, because that depends, of course, on how many infectious there are currently. And so we would have beta times t for that rate. And then we sum up overall susceptible, because for each of them it's the rate b times I of t. And then you sum up overall possible susceptibles, and that's just a multiplication by s of t. So you see the number of susceptible decreases by this factor. And of course, then for the number of infectious, it will increase by this term. So beta is the transmission rate. And the second part is, how are people leaving the infectious compartment? Well, they leave it at an exponential rate, at a rate gamma, each of them. So each individual which is infectious leaves at a rate gamma, and how many can leave at a particular time? Well, that's I of t, because you can say we sum up of all individuals, and those who are infectious, those can leave that category. So that's gamma times I of t, and then of course they have to be added somewhere. So please note, since this is a closed system, and Tom did it the same way, you don't really need to keep track of the recovered, because once you know the susceptible and the infectious, it's easy to know how many are recovered by simply reversing here the equation. You have R of t is n minus s minus I, so no need to keep track of that. And what we will do is, here in the course, we will solve this ordinary differential equation system giving an initial condition, which is there. This is the number of susceptible at time 0, and this is the number of infectious at time 0. And we will use any ODE solver available. So here's the 1R package, which can be used for that, the eSolve, but there are also other packages available which can help you do this. And of course, MATLAB is very strong at this, or Python also have functionality for this. We're not going to talk about this in this course, but we will use the DESOLVE for that. So when we use such an SIR model here, I fixed the population here to these 21,500. I use one initial infected herd, and I will use a mean exponential time here of gamma equals 0.3. And just look at how is the shape of the outbreak for different values of beta. So this is the highest value of beta. So this is the outbreak. It grows really fast, and then here you run out of susceptibles, and then it levels off slowly. This is for a bit lower value of beta. So here you not only you push the outbreak to be much later, the peak is much lower. And also this final size of the outbreak will actually be a bit lower. And this is the final version, is where you flatten it much more. So these are, for example, you can say the betas here is one way to modify the system. If you can influence the transmission rate, then you can also sort of flatten the curve, is the popular nowadays term for this. You can stretch the outbreak to last longer, it's smaller in size, and the peak is much smaller. So if you're talking about health capacity, and you say your health capacity level is at a certain level, how many you could work with, how much peaks you can still handle by contact trace and serology, or in the COVID example, like ICU treatments, then this is also something, a beta is a parameter which allows you to at least illustrate the effect of something like this. How can you actually handle this is that you need to look at to define a vector which contains your derivative. So that this is the way that the DE solve package works, that you need to define a function which contains the time, a vector, a state vector, which here y will be a vector of values, and the params is a vector of parameter values. So the first thing I do here in the function is to unwrap parameters. So I'd say the first parameter is beta, the second parameter in the vector is gamma, and also the state vector, the first component is s, and the second component is I. And then I will return a vector which contains the derivative for s here. It's minus beta s times I, and for I, beta times s times I minus gamma times I. Remember, I don't need the R part because I can derive this, so this is actually not part of the equation. I could use any numerical solver just to give you a small idea of what such a solver could look like. Is one simple procedure is the Euler method. So you can click here to get to the Wikipedia information about that if you've never tried to work with such numerical methods before, which some of you looking from the survey results probably have not. So here's a very simple method to see how to work with these. And you can say, well, we take some initial values, let's say one initial infected, the rest of the population is susceptible, so there's no immunity to start with. We define one step width, which is 8h0.1. Then we will here, the y will be a matrix where we store our results, which have a certain length. We will have 3 columns, and we will say the first one is the time, and then it's the value of s and I, which we get from solving. We will fix the initial value here at time 0. It's n minus 1 and n, just as we have up, and 1, as we defined up here. And then we simply do an iterative procedure where we always say the new value will be the old value, which is stored here, old value. So this is the old value. Sorry, the new value will be the old value. Sorry, I messed that up. Here, this is the old value for the S and I components plus the step width times the derivative. So this is a very simple, you could say, reverse Taylor method that you always take your gradient. You are in a particular point, you take the gradient, and then you follow your gradient for a certain step width. And you continue to do that. So here you get your results from the derivative function, which I just showed you. And you continue to do that until, and here said I want values from 0 to 20. So this is what I'll be doing manually, and I can call this loop, and I get the y matrix will be filled, and I can compare with what a numerical solver could do. So here's the routine from the DE solve package, which is the pink line. That's the sort of like the true result, and here the black line is the result from using h equal to 0.1. And you can, for example, try to experiment as a small exercise. If what happens if you use a bigger step width like 1, what happens then? What happens if you use 0.01? What happens then? Maybe you want to experiment with that. But this is more in the numerical department. For this course, actually you only need to know that there are solving routines for this, and how they work we will not discuss that much further. Okay, So how does the number of, here I only showed the number of infected in the graph here. And here I will show, this is the equivalent plot of what we just looked at. This is how the number of susceptible decreases. You see this is immediately decreasing here. Here it of course takes a bit longer, and they all level off at a certain point. And of course it's also interesting at which level, what will be the asymptote of this, where will they level off to? That was something which is related to 1 minus the final size, which Tom talked about, and so on. But what my point here will be is that now you have data from such an epidemic. You actually, like we have here, we have data, and we want to fit such an SIR model to such data. How are we going to do that? So there are several approaches how you can do that. So what we say, we will have observations, and will be what you will have in practice, that you will have them at discrete time points. So like say week 1, week 2, week 3, or day 1, day 2, day 3. And we will say that we want to fit our model, our SIR model, to these data. And then you can also discuss what type of data would you normally have available. And of course, we will return to that just shortly. But so if you have SNI available, then okay, you can do some least square type approach where you say, okay, yi and what our SIR ODE models is the expectation. So we will say yi minus this expectation, which is coming from the ODE model. So this is simply the solution of the ODE model, and we will minimize the square difference, probably taking a square root as well, over all our data points. So that would be a simple least squares fitting, which some of you probably have done already, those of you who worked with differential equations before. So we can use any numerical optimization routine. It's not possible to solve this system analytically for these. Well, yeah, let's get back to that at a later point. But yeah, for most practical models, it's not possible to solve this analytically. Okay. However, here I said we will have observation on S and I. Again, remember R is for free because that's deterministic derived from the others. But however, we usually don't know the number of susceptibles from the beginning. Often we only know I of t, so we don't have the S of t. But then we would just sort of say yi is simply the IT component, and we would say what we take from the model is the IT component from which we get from our fitting, right? So here would be that we say, well, the observed value of ITI is what we get here from our, this would be the output from our, for I from our SIR model, and we will say we will have some noise, homoscedastic noise. Part of that we will say it's a normally distributed random noise, but with the expectation or the mean of the observation centered around the output from our model. So this here will be the solution from our ODE model, and we will have some noise to allow fluctuations that sometimes you observe more, sometimes you observe less. So even though this is a deterministic model, as I said here, you always get the same result with the same parameters. We add a stochastic component by saying, okay, well, the mean structure is deterministic, but the observations allow for a little bit of noise. So this is one way to make a deterministic system actually a bit stochastic and say, well, that's where the noise comes in. It's in the observational part, not in the state part. And we can fit data to this. So sometimes you can then think about whether it's useful to have homoscedastic noise, because that means that every difference counts the same, no matter if you have very small values or very large values, then it's the same penalty that you impose because it's the square difference or the distance that you're penalizing. So sometimes it might be useful to maybe take a square root transform of the observation and then use a homoscedastic component, and this relates to the Poisson distribution on the next slide. So this we already had. This would be one way to do the log likelihood function. I'm just taking the simple case here is the solving function from before. So that's the soda, which is a function to solve ODEs. You give it initial value, the times the function which contains the derivatives and the parameters, as we just saw before. I'm just gonna this is maybe not so relevant for the course here, which simply say we are not going to take a square root difference, square root beforehand. So we say, well, it's a normally distributed. Here are the data that we've seen, which is from the classical swine fever outbreak. And we say the mean is now the I column of our result. And we will simply say here the homoscedastic component is not so important here for the fitting part. We can just fix that because that's going to be a separate estimation part, which will not affect here the results directly. And then we can, again, using a numerical optimization routine, as we did in lecture A, or we say we're given some starting value, and here saying that this is the log likelihood function. Please note that the starting values here, again, I use this little trick in order to restrict the parameters to be positive, which beta and gamma need to be. The theta is my parameter, but the parameter which I actually use for the differential equation is x of theta, which means that I'm actually parameterizing this by log of beta and log of gamma in order to ensure once I take the exponent, I'm always having a positive value, which is important. So the numerical part of the optimization will work without any problems, right? And that also means that once I get the result, I also have to back transform them. So this is x, this is beta hat, and this is gamma hat. And if I want to, I can also get an estimate for R naught, which is derived from equations as Tom showed. Okay, and what I can, of course, then also do is once I have a maximum likelihood estimator, I can then plug that in again into my ordinary differential equation system, and I will get a trajectory for fit with the fitted values, which I will get out of it. And I can look at that here in my example outbreak, the classical swine fever outbreak. So remember, red was the observed data, and blue is the least square fit, and then there's the square root transformed. Doesn't make much of a difference here. We can look at that, and we will see that this model is not fitting these data very well. And now, of course, the question is, why is that the case? And I will invite you to discuss that as part of the online lecture, which takes place on Tuesday, where I will try to experiment with the breakout rooms. So I will divide you into small groups, and then you can discuss with your fellow students of why this model is not very well fitting. So maybe you want to have a look at that. So you have something to discuss for that. Great. Again, assuming Gaussian, this observation is typically very often done, but it's worth to remember that small counts, that it's actually counts that you're observing, and if in the small setting, maybe the Gaussian observation is not so adequate, because if, for example, it even allows probability mass on negative values, which of course cannot happen here. So sometimes you use instead a Poisson distribution. So you say the expectation that you're modeling is a Poisson distribution instead of this is a Gaussian distribution with some extra variance, and then you get a different likelihood term. It's just maybe to state that, well, that's also one way to do, which takes the count data into account, but please note that the penalty function then you're using is a bit different than the one which you have for the Gaussian case, unless you do the square root transform. And one important feature is also that in the Poisson distribution, expectation and variance are to be the same, and sometimes that is adequate and sometimes that's not. So at least it's one thing to consider if sometimes you need additional over dispersion as well for this. So you want to have add some extra variance, and then you can do quasi likelihood and stuff like that, but that's not going to be covered in this course. The important part is to say, well, maybe you want to take into account the count data nature if you have at least smallish counts, and you can look at here, but for this here, this is the blue line or the magenta line, and you had the least square fit, the green one, with the square root transform. There is not much of a difference between these two fits. They're still not very good. You get estimators in all cases here for beta hat, gamma hat, and R naught in this case. So here there's a here you say you have that the number of secondary cases expected, the average number of secondary cases in a totally susceptible population will be 1.1 in this case. right? But estimates here for the Poisson are more or less the same, right? So I'm also, and this is related to this part here, why isn't it not fitting very well? I gave you a small exercise as well to study the flatten the COVID curve blog post. So you can just click on the link in the forms if you want to, and try to experiment a bit with different intervention strategies. And you should, if you want to, but that's voluntary. There's also a nice overview blog post, which is very non-mathematical, you can say, about the hammer and the dance. And this is something which is also related to outbreak. How can you do outbreak management? And here with the classical swine fever with the data, but you can discuss also for the COVID outbreak. Yes, so that was the part 2 of the lecture, the deterministic SIR model, and I will then continue with part 3 in the next video. See you in video 3 in the part C. And I'll turn this one here off. Okay, see you.